Today we continue to talk about transonic flow and models allowing us to calculate such type of flow. Last time we discussed how to transform potential equation for compressible flow, how to separate most important part from less important, and we came out with equation 18, which describes a simplified model of potential equation for compressible flow. It has some part which differs it from Laplace's equation. Is the coefficient which is 1 minus m square, m infinity square, and this is a constant for any particular task with constant flight velocity. Let's see how big could be this value. For example, our flight velocity is 0.3, where compressible flow starts. So if Mach number is equal 0.3, then 1 minus m in square would be 1 minus 0.009 is 0.91. This coefficient 0.91, very close to 1. Before the second derivative on x direction, and then near y direction we have coefficient 1. Let's take another example. For example, Mach number is 0.5, then 1 minus m in square would be 1 minus 0.25 is 0.75. 0.75. Such coefficient is still quite big, right? So for compressible flow, such equation would be significant when we approach to transonic flow to Mach 0.8. Let's see how much would be. 0.8 in square is 0.64. M 0.8, very close or starting transonic flow. And 1 minus m in square would be 0.36. Already a small value. So such comparison of 3 different coefficients before second derivative on x direction show us that for compressible flow and especially for transonic flow, change of equation 18 with respect to incompressible form is significant. This is why we cannot use pure Laplace's equation to calculate compressible flow and also transonic flows, because it will be absolutely inaccurate, because equation in front of first part, in front of second derivative on x direction, is significantly different from second coefficient, which is 1. Such an equation describes for us compressible flow around aerodynamic body, right? And as solution, we receive potential equation, which after could be easily transformed to velocity components and could be transformed to other properties according to the entropic nature of the flow. Unfortunately, such equation is not very accurate, as we will see in future with respect to equation 16, since we neglect many parameters. We consider them small, but once we summate all this right part of equation 16, it becomes significant in several cases. So for practical applications, equation 18 is not always good as we would like to have. Okay, it's good for many cases, but not perfect for all possible cases. This is why in 1930s, 1940s were developed such called compressibility corrections. Such compressibility corrections are having its purpose to improve quality of solution of this equation and to have data more close to real experimental data or real flow data. An approach, there is a mathematical approach to find correction for equation 18. Here, equation 35 is identical to equation 18, just substitute 1 minus m in square by beta coefficient, just a mathematical constant before secondary rate of potential function on x direction. And if you will follow the book, you will see that Anderson shows that this equation 35 is similar to Laplace's equation, and in many cases could be transformed in a sort of Laplace equation. So we can find correspondence between potential equation for compressible and for incompressible flow. And because of this, we can compare these two cases using so-called compressibility correction. The simplest compressibility correction is shown on equation 51. This is a correction of pressure coefficient. Is working on the following way. For example, we have pressure coefficient for incompressible flow, and we have known Mach number, compressible. So pressure coefficient for compressible flow would be a ratio between incompressible pressure coefficient and this compressibility coefficient, 1 minus m squared. This is how just knowing pressure coefficient for airfoil for incompressible flow, we can obtain same pressure coefficient for compressible flow. This is valid for all points over the airfoil. I would like to remind you that pressure coefficient is a distribution of points. It's not just one value, right? It's a function. Cp is a function of coordinate on upper and lower side. So this equation 51 also is giving us a function of Cp distribution with these compressibility corrections implemented. Since we know that the denominator of function 51 is just a constant, we understand that Cp and Cp0 would be proportional curves with the proportionality coefficient 1 divided by this beta. Same approach can be used for lift and momentum coefficient, as you can see on equation 52 and 53, where lift coefficient CL0 is a lift coefficient for incompressible flow, CL already lift coefficient for compressible flow. And we use compressibility coefficient, compressibility correction with according to flight Mach number. Same for momentum coefficient also works, proportional. And this was one advantage with the in theory of aerodynamics, because it allowed to calculate structures which would fly in compressible flow. As I already told you, this compressibility coefficient is quite simple. So its main advantage is that can be easily calculated or recalculated. Pressure coefficient distribution, lift coefficient, momentum coefficient. But disadvantage of this simplicity also exists. It does not describe precisely all flow processes. It's a very simple coefficient, just a linear one. And unfortunately, is not working for all possible cases. There are other improved compressibility corrections to overcome this disadvantage. These compressibility corrections were mostly used during design of airplanes for Second World War. So they are quite old, probably 80 or 90 years old, these compressibility corrections. And there are two most famous corrections. There are more in the literature, but two of them are most famous. The first one, which is equation 54, is it's a Carnot sign correction, equation 54. And we see that now pressure coefficient would be proportional to Cp0 as before for incompressible flow. But also in denominator, we might find the construction or structure describing behavior of pressure coefficient as a more complex function with respect to previous one. We still have our m infinite inside function, and we have also Cp0 in denominator of this function. And try to find its this function is more complex, but for some cases it describes better pressure distribution, pressure coefficient distribution as a consequence, velocity distribution, and lift. And there is another more complex shown on equation 55 is a latent correction. This latent correction already involves gamma, adiabatic coefficient. That also involves Mach number of light, and also involves pressure coefficient in denominator and some part of fraction of denominator. Latent correction, which is longer. We must understand that equations 54 and 55 are purely empirical equations. They are not related directly to solution of Laplace's equation or solution of potential equation for compressible flow. They are a result of processing of many experimental data, and for some experimental data, for some airfoils or for some airplanes, Carnot sign correction is better. For another, latent correction is better. For some cases, also Prandtl-Glauert correction, the first one, which was the simplest one, is Prandtl-Glauert Cp0 divided by square root 1 minus m infinity square. This was Prandtl-Glauert correction from previous slide. It's not here. For some aerodynamic bodies, is better this function. Which one to choose is a question of experience. Probably has to base on analysis of similar data, similar aerodynamic structures, and then to choose a correct formula for compressibility correction, pressure coefficient. On those days, of course, we had no computers available. It was not possible to calculate numerically pressure distribution, pressure coefficient distribution. And nowadays, probably not so much important, these compressibility corrections. You might think not so much important, but these corrections could serve for you for your future work if you work in aerodynamics as validation. It's a validation point because these formulas were developed based on many experimental data, and they can describe, not perfectly, but in acceptable accuracy, distributions or flow properties on the aerodynamic bodies. Okay, please let me know if you have questions. Don't forget to write in the comments or ask by voice. I hope more or less clear this aspect. Compressibility corrections were very important on the design of real aerodynamic structures because it was the only way to calculate airplanes, airfoils, or wings for compressible flow conditions. Nowadays, since we have CFD software, we can use this CFD software with the great success. But also for CFD software, as you know, we need reference data or experiment or analytical models. And in this case, such corrections would be this possible reference point. Next topic I would like to talk today is a critical Mach number. Let's see several cases to understand the idea of critical Mach number. These cases are shown on figure 5. So let's see on figure A. We have an airfoil, arbitrary shape airfoil, which flies with Mach 0.3 m infinite. And locally, we have a distribution of velocity on this airfoil. We know that on front part of airfoil would be higher velocity because pressure drops. And on the bottom side, probably would be lower velocity because pressure rises, right? At some point, point A, arbitrary point, for 0 and positive angles of attack, this point A is always located on the upper side of the airfoil. We will have a highest Mach number for all these tasks. Highest Mach number will happen because pressure at this point would be the lowest possible, called maximum Mach number, right? So maximum Mach number for airfoil shown on figure A is 0.435, where infinite Mach number is 0.3. We see quite significant increase of local Mach number with respect to infinite Mach number. Once we will fly faster, our local Mach number will also increase. For example, we see figure B shown on the right top of the screen. We see when we are flying with the Mach 0.5, our local Mach number at point A is already 0.772. So approximately 50% higher than infinite Mach number. I would like to tell you that point A is not fixed on the airfoil. I'm quite sure that point A is changing, but probably is changing insignificantly because we, for different Mach numbers, we can observe variation of pressure coefficient distribution. And because of this, this local minimum of pressure distribution corresponding to local maximum of Mach number also is changing. But for my opinion, it should change insignificantly, more or less on the same point. For example, it cannot go on the back part of airfoil, cannot go to the lower part of airfoil. It stays more or less on same location, but can change. Once we will try to increase more Mach number at some specific moment, we look now on figure C. At some specific moment, we have locally Mach 1. So acceleration of flow happened. And we have Mach 1, speed of flow is equal to speed of sound. And this happened at some specific Mach number and infinite, which is called critical Mach number. In the case of our example, it's Mach 0.61. This critical Mach number is the Mach number of flight at which locally we obtain Mach 1 at least one point, of our airfoil on the surface of our airfoil. What happens next further if we will try to accelerate more than 0.61? We can see figure D. In such case, already we have a region with the supersonic flow, which you can see on figure D. And for example, at Mach 0.65, we will have such a shape of supersonic region where there is also, it is possible to identify a sonic line where Mach is equal 1. Inside this bubble, Mach will be supersonic. Outside of this bubble, Mach number will be subsonic. Why we are talking so much about critical Mach number? It's mainly because flow changes significantly when Mach number locally becomes supersonic. And these changes happen in the flow. They are drastically change flow picture, and they drastically change the coefficients of performance, drag and momentum coefficient change. Because if you remember, transition from supersonic to subsonic regime cannot happen smoothly in all cases. For example, in case of airfoil, we will have a shock wave. And this shock wave will be located somewhere at the on the border between supersonic and subsonic region. Okay, inclination of the shock wave we can determine depending on infinite Mach number. This shock wave is not linear, is not something that is just a line, as you know, since we have a boundary layer and shock wave on real flow. This shock wave would have a complex structure. Also because our airfoil is not linear, is not a simple line, right? It's curved. This is why flow around such airfoil would be complex as well. So we pay a lot of attention at this moment of figure D, because when it happens, we have a shock wave. It means that we must sustain the shock wave. We must spend extra energy, additional energy to sustain such kind of flow. Shock wave is characterized, as you know, by losses of energy. So we will start lose energy just having shock wave without producing any useful work. These losses, something we do not want to have. So we will try to avoid flow shown on figure D, and we will try to work and to fly at velocities close or equal to critical Mach number when supersonic region does not appear. Flow is everywhere subsonic, compressible, and the flow is theoretically asentropic. So our losses are minimal. You know, lift to drag ratio is quite high. So this is what we want. We want to work in case C, and we do not want to work at case D. Just losses without any useful work. Maybe flying a bit faster, but no sense because we lose so much energy just to fly faster. Analytically, we can determine presence of this local Mach number, Mach 1, and we can define where, at which exactly flight velocity will start to happen this local Mach number 1. To determine such state of critical Mach number, we need to solve one equation. It can be solved numerically or can be solved analytically, probably in some cases. If, let's say, if pressure coefficient can be described by analytical function. But in most cases, this equation can be solved numerically without any problem because it has just one extremum or one solution. So what is this equation we will try to solve to determine critical Mach number? This is equation of equilibrium between isentropic flow and compressibility correction calculated by potential equation. First part, isentropic flow relation, is shown on equation 58. This is a function, I think we already saw it in our previous discussion. It describes pressure coefficient at arbitrary, absolutely arbitrary point A, and its relation to pressure at infinite distance. I think equation 58 we already had before. It's let me see somewhere. Maybe I will not find. It's right here. Equation 1122. Pressure coefficient written in terms of Mach number and pressure ratio. It's equation 22. For this equation 22, we will use pressure function as function of Mach number and infinite pressure function as a function of infinite Mach number. For both of these pressures, we have an assumption that P0 is constant. Okay, P0 is constant. It means we are working in isentropic conditions. So we have no losses of pressure since we do not have shock wave yet. And our boundary layer is very weak, so we neglect presence of boundary layer. We use P0 constant, and according to isentropic relation, we use formulas from isentropic relations, which you already saw many times. For example, for calculation of flow properties in compressible flow, calculation of flow properties inside nozzle, same function. Same pressure function. Maybe I can find it also in this chapter. No, it was on the previous chapter. Sorry, but it's the same function that is also tabulated in Appendix A of Anderson book. So we have this function written as a ratio of pressures. We have ratio of these functions. Power is same gamma divided by gamma minus 1 for both functions. So we simplify in such case. This is general formula for any Mach number at point A. When we are trying to search critical Mach number, instead of MA, we will put just one, value 1, and equation will simplify. It will be just a function of M infinite related to pressure coefficient. And here it is. Equation 59 is simplified version of equation 58 when we substitute MA equal 1. Plot of equation also, okay, we call, instead of M infinite, we call this Mach number M critical. And this is equation 60. Absolutely same equation as 58, 59 is equation 60, where M infinite is substituted by M critical and MA is substituted by 1. We can plot this equation, pressure coefficient versus M infinite. It's a function of just one parameter. You can see this equation plotted on figure 16. This curve here is shown, right? And another equation we will use to find our critical Mach number is the compressibility correction. Equation 51, 54, or 55. These compressibility corrections we just saw on previous discussion. One of these three equations as a pressure coefficient distribution. 54, 55, and general Prandtl-Glauert correction, which are also functions of M infinite or M critical, and CP0, which is known value for incompressible flow. So we can plot one of these equations describing compressibility corrections. I will write here that they are compressibility corrections, which we saw on the previous slide. And it will be somewhere intersection of these two curves. Right? This intersection will correspond to critical Mach number. This is how analytically can be found the value of critical Mach number. Let's take a look what we involve to find this solution. From equation 60, we involve isentropic nature of flow around airfoil when still we have no supersonic flow. From geometry of airfoil, we involve equation 51, 54, and 55, which are already incorporate geometry of airfoil inside CP0. CP0 is inside of any of these equations, and it describes for us, it's a characteristic of geometry. So geometry is inside the CP0, even if it's constant. In such way, we involve both geometry data and nature of flow, isentropic flow, and we find exactly point of critical Mach number, which corresponds to Mach 1 at some arbitrary local point. For different types of airfoil, since I told you that compressibility correction is already incorporating the geometry of airfoil, for different types of airfoil, different thickness of airfoil, different shapes, not only thickness, this CP0 will be different. And as a consequence, curves describing pressure coefficient for different airfoils with respect to Mach number will be different. You can see here for thick, for example, and for thin airfoil. We know that for thick airfoil, pressure coefficient CP is always higher because thick airfoil produces higher pressure range, higher pressure ratio, and the higher lift. This is why, as a consequence, higher pressure coefficient results for us in a lower value of critical Mach number. Here, for thick airfoil, Mach critical will be smaller, and for thin airfoil, pressure coefficient is always smaller, lower, and because of this intersection will happen further, and it will have critical Mach number higher. This is a proof why thin airfoils are flying faster than thick airfoils, because thick airfoil have sooner critical Mach number, or critical Mach number for thick airfoil is always smaller than for thin airfoil. This is why we cannot use thick airfoil for high velocity applications. Thick airfoils are more performant than thin airfoil, but they are better for low velocity flight. If we would like to fly faster, so critical Mach number will be bigger, we need to use thin airfoil. It will be not so much efficient, lift to drag ratio would not be so high, but we can fly faster. Always there is a trade-off, a payment. If flying faster, spend more energy, spend more fuel, more expensive. Flying slower, better from economical point of view. This is why all planners, modern planners, you saw probably that there are airplanes more looking like planners with the very long wings, which can fly 24 hours, 7. So they do not need to land with the solar panels on the top, right? They fly all slowly because slow flight is more efficient with respect to fast one. But fast flight is also important. This is why we have such different types of airfoils. Fast flight can be more important for critical applications, for example, fast delivery, fast transportation. In such case, it will be cheaper to fly faster than to fly slower. For example, who would like to spend 2 days inside airplane flying from one continent to another? No, it's better to spend just 1 day flying fast, right? And so you it compensates. It compensates. There are many aspects to evaluate from this point of view, financial point of view, and it doesn't have direct relation to aerodynamics, but I would like to give you this at least idea why efficient flight is not always good, and vice versa. Why efficient flight is essential in several cases, right? Okay, I hope it was clear about critical Mach number. Please let me know if you still have some questions about this problem. Anderson also shows some examples about pressure coefficient distribution and critical Mach number for different airfoils. For example, for Mach 0012, at zero angle of attack, we can find pressure coefficient, the minimal possible value. This is minimal pressure coefficient is interesting for us because it corresponds to highest Mach number at this specific point. So this point is having highest velocity. Once we see CP distribution, we do not need to analyze all possible points, all possible positions. We just need to take a minimal point. Pay attention that axis here is reversed, so higher values are below and lower values are above. So we take minimal. It's written minimal, but it's on the top. So we need just one point when we analyze critical Mach number for some specific angle of attack. Also, Anderson shows how to solve examples, how to solve for any particular airfoil, analyzing from point of view of equations, just calculation, nothing more technical, just calculation, but calculation showing how to obtain critical Mach number for this airfoil. Also, there is another old method, let's say a graphical method. When you approach from one point to another, nowadays is also important. You do not need to calculate all possible variations of Mach number. You need to find where is local value of critical Mach number, right? Let's say maximum of, let's say, where left-right of equation is closer to the right side of equation, and then work inside this region to refine inside each one in a such way. For example, 0.72, 0.73, and 0.74, these are three first attempts of calculation, just three calculations. We take left side of equation, which is compressibility correction, according to Prandtl-Glauert correction, and the right side of equation is asymptotic flow. We calculate for both three, for all these three cases, and we find at which case we have better correspondence of left side of equation and right side of equation. They should be equal once we find solution. And then we define that it's between 73 and 74. We refine more this region. We find, look here, with these two values, 738, 737, and making some interpolation, we find out that this value, according to interpolation, is the solution. And then check it, calculating left and right side of equation. As I told you, 4-digit numbers are more than enough in accuracy of technical calculation and aerodynamics calculation. So you see that they totally correspond, left and right side of this equation. So it means that critical Mach number is found correctly here. So graphical method also, when you plot two curves and find intersection between two curves. This gradient method, when you approach step by step to solution. Also brute force method, when you just calculate all possible variation, which is not the best from time point of view. There are different ways to calculate this critical Mach number. I hope if you need one day, you will choose your own method which corresponds to your available time, computational resources, and instrument. Also, Anderson shows analysis of pressure coefficient distribution for NACA 0-12 for different flight regimes. For example, for left side picture, Mach 0.575 is here. Pressure coefficient always or did not cross critical pressure coefficient. It means that in all points of the airfoil we have just subsonic flow. Okay, critical Mach number calculated by method presented before. We compare critical Mach number with the pressure coefficient distribution. We see there is no intersection, so will be no local sonic flow or supersonic flow. In case B, 0.725 pressure coefficient, and also correspondingly increased Reynolds number, because once we increase Mach number, we also increase Reynolds number with velocity. We see that there is one point of intersection. It means that locally will be pressure coefficient critical, and locally would be Mach equal 1. I hope more or less clear this part. Another question Anderson explains is drag divergence Mach number sound barrier, showing drag coefficient variation with Mach number, especially in approximation to critical Mach number. We see here this CD distribution for incompressible flow. It's points A, B with the drag coefficient constant CD 0. Then from B to C, we have compressible flow, but no variation of drag coefficient. This might happen, this might not happen, depending on geometry of airfoil, but in most cases it will not happen because flow structure remains azentropic. There are no losses, and drag is something that characterizes our losses. And starting from critical Mach number, we receive locally supersonic velocities, starting from point C. Then this region of critical Mach number, region of supersonic velocity increases, grows, and also grow shockwave behind this zone of supersonic flow. Bigger is Mach number, bigger is the shockwave. And from point C to D to E, our Mach number increases. Then these shock waves, they start to prevail, and at some point they start to join. Our shock waves will start to join and will go in front of airfoil or in front of the wing, and they form so-called sound barrier. Shock wave joins and becomes a bow shock wave. In such point of Mach 1, we have maximum possible concentration of, let's say, loads or relative loads. Let's say relative loads because they are relative to dynamic pressure and they are relative to size of our body. So maximum concentration of relative forces, which results in point G, a maximum of drag coefficient, and then from point G to point H, we accelerate. Our shape of shock wave is also changing. It detaches and deforms, and because of this, also changes drag and drag coefficient. One important comment here, that even looking that drag coefficient decreases, goes down, it does not mean that drag is decreasing. It's just drag coefficient decreasing, right? Because CD is drag divided by m infinite. Okay, let me write here. Okay, I will multiply by 2. I will divide by density, and most important, m in square, speed of sound in square, and also area. Okay. This is a definition of drag with respect to Mach number, not with respect to velocity. You know that all this one divided by 2 is just dynamic pressure. And since we are plotting of the coefficient versus Mach number, I wrote in terms of Mach number, m infinite also here, and a infinite. So even though drag coefficient decreases, Mach number compensates. It increases significantly. So it means that total drag still continue to increase, not to decrease. Because we have Mach number in square, this Mach number is bigger than 1, so it increases more faster than decrease of drag coefficient. So drag always goes up with increase of Mach number. Do not lose this point when you will calculate something in supersonic velocity. Decrease of drag coefficient does not mean decrease of drag. That's it about the change of or behavior of drag coefficient for compressible transonic regime and supersonic regime. Then after we go to supersonic regime, starting from Mach 1.2 until almost hypersonic flow, or until hypersonic flow, drag coefficient stabilizes. It will be a constant value, which will give us another advantage, that aerodynamic body can be tested or simulated at low supersonic velocities, but already with stabilized drag coefficient. And for any other supersonic velocity or even hypersonic velocity, drag coefficient stays constant. This is an advantage. We can test or simulate aerodynamic bodies at lower Mach number and then use same data for high supersonic velocities or even hypersonic velocities. Okay, very nice picture. I like a lot this picture. It's beautiful from artistic point of view, and also it looks very nice from engineering point of view. It's the first manned airplane which flew faster than sound. Very nice. October 1947. Such an airplane used not a conventional propeller engine as you see, but it used ramjet engine. Or okay, the engine which utilizes idea of ramjet. Another important information we see from the book is this figure, is essential figure, which explains the best thickness to chord ratio of airplane, or let's say which should be the thickness of airfoil or the wing for different applications, for different Mach numbers. for subsonic and for supersonic application. This region here, which you can see, is based on real airplanes. You can see that if we fly with subsonic velocity, our thickness is significantly higher than for supersonic. I will try to make a line here. Is it straight? Probably. Okay, more or less just to separate two zones. We can see that starting from 6% to very high, 14%, 15% could be the thickness of airfoil or wing thickness for efficient application inside the airplane. Why it's important, this figure? Because it's based on real airplanes. If you start your own development, you can use this as a reference. So you do not need to do optimization from point of view of choice of thickness of your wing or thickness of your airfoil. You can already choose something that exists and proven its efficiency, because development of such airplanes cost billions of dollars. So huge, very intensive studies on airfoils, wings, and many aerodynamic parameters have been done already. Why not to use these results for new development as a basis for from the old experience? It's always useful. It's priceless now, actually. And for supersonic velocity, we can see that there is also a range of thickness depending on flight Mach number, starting from Mach 1 to Mach 2.5. And also there are some points which are not inside this range, like SR71, which is very special, right? Very special, or F14, very special aerospace structure, not exactly fitting inside this paradigm. So thickness for supersonic flight is small. It's at most 10% for Harrier 2, but I think it's more acceptance than a norm. So if we would like to fly in supersonic velocity from 1.5, we see that between 4 to 6% thickness could be used efficiently, because there are structures proven its efficiency with this thickness. So it's a guide, some sort of a guide, how to choose a correct aerodynamic structure, at least how to choose thickness of wing or airfoil to fly efficiently. Sorry. Okay, I see no questions. Another way to increase efficiency and to fly faster is so-called swept wing. What we like in thick airfoil, as I told you already, thick airfoil is very good because it's efficient, but unfortunately, thick airfoil cannot be used for high velocity flight, cannot be used. But if we would like to keep efficiency of thick airfoil, we can just incline the wing, whole wing. For example, here on figure 14, we see this wing inclined 45 degrees. Cross section normal to the border of this wing is still thick airfoil, is the same as you can see on figure A. So it has all the properties of all advantages of thick airfoil. But being inclined and now building projection of this wing on flow direction on figure B, we see that thickness of this wing is significantly smaller, so it can fly faster. Swept wing is the wing which is inclined with respect to flow direction to some angle. Swept angle can be different, can be small for a few degrees, or can be optimal, like 30, 40 degrees, could be higher for higher velocity flight, and depend on the inclination. Of course, all aerodynamic characteristics would change. Technology of sweeping wing or swept wings are used to improve the efficiency of high velocity flight. So we are utilizing same time advantages of thick airfoils and advantages of thin airfoils, flying faster with less energy losses. How to take into account such wings is, or how to calculate is shown on next slide. One example of airplane with swept wing is shown on figure 15. And I think you saw such airplanes everywhere in any airport nowadays. Such airplanes are used for commercial flights. All airplanes have swept wings nowadays. All commercial fast airplanes. Right? How to take into account by simple mathematical model. Here we see equation 66, 67, 68, which describe lift slope for such wing. I would like to remind you that lift slope is inclination of the lift line versus angle of attack. So I have CL, I have angle of attack, and this is my lift slope, A0. This we had for incompressible flow, A0, right? But for compressible flow, we can use same concept as a compressibility correction, A0 for incompressible flow, for compressible flow, A-comp. Let's see how different it is from A0. We see in denominator some value which is smaller than 1, right? It's used for subsonic, of course, for subsonic applications. So Mach is some positive value, 1 minus Mach would be some value smaller than 1, and this A0 divided by geometry. This is a geometry. I think it's a taper ratio and aspect ratio. Characteristics of the wing, relation between size of the wing on the tip and size of the wing on the root, and aspect ratio is a relation between area of square and area of the wing. Area of square occupied by the wing. I think it's okay. I hope you remember if we define this distance as b. So aspect ratio is it's b in square. Probably it's b in square divided by area of the wing, planar area of the wing. It's always bigger than 1. Bigger than 1. It's positive. Some value 7, 10, depending on airplane. 15. So by aspect ratio and taper ratio, we define geometry of the wing, and also these corrections presented on on equation 66, 67, 68, they are empirical, they are not analytical solutions. 67 is more complex, and 68 is even more complex. It involves inclination for the swept wing is cosine of lambda. This lambda is here. Sorry. coincides with the airplane by itself. So this angle, swept angle between normal direction to wind relation to wind and wing direction. Okay. Also, 68 is the most complex equation, but again, this equation is a sort of approximation. It's not an exact solution of flow relations. Okay, please give me a second. I will take a glass of water, and if you have some questions, please ask your questions. I will leave here previous slide. Okay, I'm back. I see no questions asked in the group. I would like to make our today class shorter. I will explain probably the last topic for today. It's very short, called area rule. What is area rule? Once we build aerospace structure, and especially which would fly with a supersonic velocity, we might have a problem that strong shock waves appear even on airplanes of quite sharp shape, right, quite thin. We have losses. We can have significant losses. So area rule is a way to decrease possible losses, increasing efficiency of flight. Typical airplane is shown on figure 16. Here is plane view from the top. There is a cross section, BB, and there is area distribution along the axis. You see that first area is small. Then when wing starts, area is constantly increasing because area of the wing is changing. And then this area distribution, this area change, causes constant appearance of new shock waves. Why they appear? Because area is not constant of airplane, and area is increasing. So flow is compressed more and more and more along the axis, producing more and more compression. You increase intensity of shock waves along the airplane. From point of view of energy balance is not good, and it was proposed long time ago, such a strategy to keep constant area. For example, such constant area airplane could be seen on figure 17, schematic of an area ruled aircraft. The idea is the following. Once we increase area of the wing, we decrease area of fuselage. So our fuselage is reducing and the wing is increasing. In such a way, we keep constant area along most part of the airplane. In such a way, we generate only intensive shock waves or at the first part of airplane where we have significant change of area. after area stays constant, we just redistribute these shockwaves in and we create zones of shockwaves compensated by zones of expansion. So we just redistribute energy. We do not create high energy anymore along long distance along the axis. Such strategy leads to significant drop of maximum drag coefficient on the airplane. You can see on figure 18, airplane without area rule and with area rule. How much is this difference? It depends on complete structure of airplane because it's three-dimensional, cannot be expressed analytically, but can be found that area-ruled airplane could be 30–50% more efficient on transition on sound barrier than non-area rule airplane. So this is a significant difference. And because of this, nowadays, most of supersonic airplanes which has to cross air barrier are designed according to area rule. We must understand also that area rule is not something which is described by mathematical model. It's more an idea how flow is moving from one region to another, how flow is behaving in transition from subsonic to supersonic regime. It should be clear that area rule is not proven by model or not created by model, not described by model. Area rule is an idea which, for my opinion, nature follows this idea of minimal energy losses. In such way, we can create more efficient structures. Please let me know if you have questions about it. I think for today we can finish because next task, supercritical airfoil, I would like to start from Thursday, and next time also we will finish chapter 11. We will go already to chapter 12.